Okay, so in the last class we were looking at JPEG, and before that we had seen GIF. What we're going to look at today is yet another format, PNG, and as part of that I want to look at the concept of transparency. So we saw that GIF allows one of the colors in the color lookup table to be transparent, so you can see through it. So you could see through transparent pixels. They would have the color of the background that they appear on. So if they're on a web page and the background of the web page is blue, those transparent pixels would be blue. Okay. In GIF, pixels can only be transparent or not transparent, which can cause problems where the edges are more subtle. JPEG, it doesn't support transparency at all. Just doesn't do it. Now, transparency is often more complex than just being visible or invisible. So if you look at this pen here, there's a shadow behind that pen. And that shadow is interacting with the beige paper that this pen appears on. And so the dark shadow is making that beige, dark beige. If this pen appeared on a pink page, then that shadow here, the shadow here, would be making that pink look dark pink. So the color that you see will depend on the transparency in the image and also what's happening behind. So it's not that you're not just seeing the color that's behind, you're seeing it interact with the transparency. Similarly up here, for example, this stamp here is interacting with the background. And these pixels here, if they were on a different color background, would appear different. Here, the shadow in these keys are interacting with this partially transparent stamp, which is interacting with the page behind it. And there's a couple of things going on there. So in the examples you're looking at in this image, the transparency isn't simply all or nothing. There's degrees of subtlety. Okay? So some applications require transparency. So if you have an image on a web page and you don't want it to be rectangular, for example, you want to see some transparency there. In Photoshop, you need transparency. And when you're putting parts of an image onto another image and making it look like it belongs there, you need some transparency there as well. So you may have seen this in Photoshop already when you're messing in Photoshop. So images in Photoshop can have layers. And a layer is like a pane of glass where you have multiple planes of glass, one on top of another, and as if they're painted onto, and you can see through the parts that haven't been painted onto what's underneath. So in this image here we have like the Kodak, this graphic in a different layer, and this tile in another layer. And in Photoshop, this grey and white checkerboard pattern means that the pixels are transparent, and so you can see through them onto what's going on behind. Here's a picture of me many cheeseburgers ago, and you can see we've got 3 layers here. Okay, so there's the background layer, which has the Arc de Triomphe. There's the layer with me in it, and there's the layer with text. And when you put them all together, it looks then, it actually doesn't, it's not a very convincing t-shirt. Actually, it doesn't look like there's actually the text is on the t-shirt. It looks like it's just stuck on the picture. But that is there, you can make it look like I was at the Arc de Triomphe. Now, I have actually been to Paris as well, but obviously this isn't a picture of me in Paris. It's a picture of me somewhere else. pretending to be in Paris. Okay, so each layer is like a pane of glass. And then where it's painted on, obviously you see the paint, but where it's not painted, you see through it onto what's underneath. But the important point I want to make is that the transparency isn't all or nothing. Okay, so in GIF, a color is all or nothing. Transparency is all or nothing. A pixel, you can see through it completely or you can't. Okay, but sometimes you want the transparency to be more subtle. And so here we have examples of a fairly subtle transparency where we've shadows, things fading away, and they're interacting with what's happening behind them. So in GIF, the lookup table will just say this is a transparent color. That's fair enough. How do we deal with that then in other situations? Well, transparency needs yet more data. So if you've got decent transparency in an image, then each pixel will have a color. So you could represent those with their RGB values. That's nothing new. And then the transparency could be expressed as a percentage. So 100%, for example, could be completely visible, and then 100% could be completely invisible. So if you had a red pixel, or some red pixels, and they were 50% visible, while if you display them on a white background, they'd look pink. If you display them on a black background, you know, if they were interacting with black, they'd be a different color. If they were interacting with yellow, they might have an orangey tinge or something. So it would interact with the colors that they're on top of. Transparency can also be expressed as a value from 0 to 255, and you could use a byte for that. And so typically, that's what we do. So the extra channel that we use to represent transparency, that's called the alpha channel. So you've red, green, blue, and then how visible is it? Is it fully visible, fully invisible, somewhere in between, how in between? So that's a whole other byte then that we're using for each pixel. And so this gives us RGBA as it's known. So red, green, blue, and alpha. Now, the idea is largely the same, but you know there are some variations. In some scenarios, the alpha channel gets stored first. You know, but whatever. The idea is that you've got your red, your green, and your blue, and your alpha. Okay. Which brings us then to PNG, Portable Network Graphic. I've heard some people call them pings, but I don't think that's what we do. We call them PNGs. It's a PNG. And also, if you know anything about networking, you know that ping means something else. So it's probably a bad idea. So ping was created as an alternative to GIF. GIF was very much of its time. It could only support 256 colors, but when GIF was devised, that was plenty. You know, that's all you'd be storing, that's all you'd be displaying on a computer screen anyway. So what's your problem? But as time went on, computer displays got better, our demands on image formats increased. And JPEG was great at certain things, but there were some areas where JPEG fell down a bit. Now, the main motivation was that some of GIF was covered by a patent. Do you know what a patent is? So a patent is a monopoly granted by a government to an inventor that prevents others from using the invention or importing it or selling it, typically for 20 years. So if you invent something, you go to the patent office, you get a patent office, you tell everyone about your invention, but in exchange, the government will give you a monopoly on its use. So there was a patent on I think it was the Lempel-Ziv-Welch part of the compression algorithm. So GIF uses LZW in places. And people had been using GIF for a long time and writing software to process GIFs, but the company that owned the patents was sold, and the new owners decided they wanted to be paid what they were due. And so all of a sudden you couldn't compress or decompress GIFs without infringing on their patent. So there was a bit of drama. I think in the end they said they were only looking for money from people who were saving GIFs, so the producers of the software to write GIFs, not people that were reading them, for example. But anyway, people got up in a huff and said, you know what, screw you GIF folks, we're going to make our own format. And so this is probably one of the earliest examples of maybe crowdsourcing and open source and stuff. So the community on the internet decided that they would come up with their own format. And this eventually we ended up with PNG, Portable Network Graphics. Now, as it turned out, there was kind of a need for something anyway, because first of all, JPEG didn't support transparency. It didn't do graphics very well. It was, you know, and so PNG became popular with certain classes of people. So PNG is completely lossless. Now, the scenarios in which you would need a lossless image are quite limited. Obviously, we would all like to have lossless images all the time. You know, and I'd like to have lots of money to have, you know, loads of hard disks hanging off my machine. But you know, it's inefficient to have lossy compression for pictures of you in the pub, you know, having a birthday party or something. You know, storing those at 5 times the size they need to be is just decadent and wasteful. At the same time though, if you are a graphic designer and you're working on a product for a client and it's going to be, you know, appear in magazines, very high resolution, high quality, you don't want to be messing about with JPEG. Typically what people do though is they work on something in the highest quality, and then at the very, very last step they reduce it down to whatever it needs to be. So even if you knew something was going to be saved as a GIF, you'd still work on it in Photoshop, you know, with full RGB color and do everything you need to do, and then only at the very, very end would you convert it to a GIF. Similarly, if you were working on photographs for products for a web page, you might work on them in very high resolution in full color, and then only at the last minute, the last stage of the process, would you save them down as a JPEG for the size they need to be. Okay? So some people do have an excuse for using very high quality lossless image formats. So PNG can be 24-bit RGB. So each pixel takes 3 bytes, 1 byte for the red, 1 byte for the green, 1 byte for the blue. Or it can be 32 RGBA. So you have a byte for the red, a byte for the green, a byte for the blue, and a byte for the alpha. It doesn't do animation, by the way. GIF does do animation. We might, for the crack, sometime in the labs, if we get time, do some animated GIFs just to see how they work. There was talk of animated PNGs, and there's sort of some kind of makey-uppy extension, but PNG doesn't do animation by default. You also got a variety of color options, which we'll look at. So one of the advantages of PNG, I mean, I think the people that designed it were mindful of the fact that 16 million colors was quite wasteful, especially when it was competing with GIFs, which could do small number of colors very efficiently, you know. So there's different modes of PNG. So PNG, for example, can do a kind of indexed color. So if you know you're only going to use 16 colors in your image, well, you can code a PNG in such a way that it wouldn't be vastly inferior to the GIF with 16 colors. Because if you're only going to have 16 colors, using 24 bits for each pixel would be very wasteful. So there's an indexed color option, and you can have 1 bit per channel, or per pixel in this case, 2 bits per pixel, 4 bits per pixel, and 8 bits per pixel. So whereas GIF can do indexed color with pretty much any number of colors, although you'll be looking at powers of 2 in terms of the number of bits per pixel. Oh, would you? Not necessarily, no. But anyway, PNG does 256 and then 16, 4, and 2 colors. Okay. There's a grayscale version of PNG. And then there's even a grayscale plus alpha version of PNG. So you can have a black and white image with full transparency or not. There's what they call a true color version, which is 24 bits per pixel, or 48 bits per pixel if you want to, per channel. Actually, is that correct there now? Not convinced. Not convinced by these numbers, actually. Oh, sorry, yes, of course, that would make sense then, yeah. So 8 bits per channel is 24 bits per pixel, yeah. No. And then you can have full RGB color with transparency as well. So different options. So the main thing PNG gives you that JPEG doesn't give you is transparency and losslessness. The main thing that PNG gives you that GIF doesn't is the option to use more colors. But PNGs are huge, so it's very wasteful, for example, to use them in a website, because the size of the image would be 3 or 4 times bigger than the equivalent JPEG, even the equivalent high quality JPEG. So if you see PNGs on a website, somebody has made money. Now, PNG uses an interesting kind of compression. We haven't really looked yet, have we, at predictive coding? No, we haven't. So, in predictive coding, you look at what's going on with the data and you make a prediction about what the next value is going to be. And then all you code is the difference between your prediction and what the value turned out to be. So if I was giving you, if you were the receiver, okay, and I had sent you 2, 4, 6, we might have a scheme for agreeing what we think the next value should be, and it might lead us to believe that the next value should be 8. Okay? So, as the transmitter, I'm aware that the predicted value is 8, and I know that you would predict it would be 8. Okay? So then, actually, all I send you is +1. Because I know you're going to predict it's going to be 8. It turns out the actual value is 9, so I just send you the +1. So we saw that in... we did see it, didn't we, or did we not? I think we did. We had a look at that. Predictive coding we did. I remember doing +1 and -1 and whatnot. So in the predictive coding we looked at, you kind of assume that the value is the same as the last one, and then all you code is the difference. But you can also be a bit more sophisticated, where based on the information that's there, you can predict what the value might be, and then you just code the difference. So if you knew this so if you know the colors of these pixels, right? If you know what A, B, and C are, yeah? You might be able to hazard a guess at what you think X should be. So you might think X could be the average of A, B, and C, yeah? So both the transmitter and the receiver could know what scheme for prediction is going to be used. And so then all the transmitter needs to do is to send the difference between the predicted value and the actual value. Get the idea? We'll have to Google in a minute just to check that D isn't in there and that this is actually correct. Now, so Deflate then is a compression algorithm that uses a combination of Lempel Ziv compression and Huffman coding. Now you might say, why didn't you use Lempel Ziv Welch, which is an improvement on Lempel Ziv? But of course, one of the motivations for developing PNG was that the patents surrounding Lempel Ziv Welch were being enforced. So there's no point in coming up with another alternative format that uses the same patented algorithm. So it just uses Lempel Ziv and Huffman coding. And that didn't infringe any patents. Huffman didn't patent his algorithm, despite it being one of the most useful bits of computer science ever invented, really. And Lempel and Ziv by itself wasn't patented, or perhaps the patent had expired by that stage. Incidentally, the Lempel Ziv Welch patent, the 20 years was up quite some time ago. Deflate looks a bit like this. Okay? So what it does is it recognizes repeated byte sequences. So a bit like, you know, the way Lempel Ziv Welch, you have a dictionary and if you see something and it occurs again, the way if you have like WAGGA, the next time you see it, it's turned out it has a code in the dictionary. This isn't a million miles away from that. So Deflate recognizes repeated byte sequences and then tells the decoder that they're, you know, this far back and so long. So the encoder would recognize that this pattern here of like light, you know, this sequence of bytes here would know the receiver's already seen that. You already saw that sequence. It was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bytes ago, and it's 1, 2, 3, 4, 5, 6, 7, 8 bytes long. And it's not unusual for patterns to be repeated. So go back 14, copy 8 bytes, and then repetition in data then can be exploited like that. Any questions? So that's GIF, JPEG, and PNG. And you should understand now for each of those how they're represented in the computer system, how the color works, how the compression works, in which situations is one preferred over the other. So if you're made of money and space is no object, you know, PNG is always the best choice. Then when you're constrained, well, actually no, because if you want animation, of course, GIF is the best choice. But if you're constrained otherwise, then as well, you may want to make different choices. Photoshop stores not only the red, the green, the blue values and the transparency, but of course each layer also stores, you know, RGBA. So each layer in Photoshop has a red, a green, a blue and a transparency value for each and every pixel. So that's why Photoshop files start to get really, really big. Each new layer is a whole new set of values. Now you don't save Photoshop files for viewing on the web. You flatten the image and save it as a PNG, a GIF or a JPEG. Any questions on any of that? Okay.